All right, so today I will talk about composite operators and how to deal with them, in particular how to renormalize, how to use the so-called operator product expansion, and the properties of their renormalization, in particular anomalous matrices and RG equations. So composite operators are really important objects. So fields depend on some position, but a composite operator is something that involves more than one field that nevertheless is defined at a single point. That can we can guess that will give us divergences. For nothing, if for nothing, just think of the 2-point function of I mean 2-point function of the field that is divergent in X space, like 1 over X minus Y to some power. So having these composite operators implies introducing some new divergences into the theory. And these composite operators are objects of interest and importance. Examples are the energy momentum tensor, or in gauge theories, particularly in QCD, something like fermion or quark condensates, psi bar psi, and so on. So the quark condensate being a measure of the vacuum of the phase in the theory. So how do we introduce composite operators into the theory? Well, we introduce them the way you introduce a field, by adding a source for them. So for the fundamental field, I would write in the path integral. So path integral is of E minus S, but then I would add integral J dot phi at X. And the same way, I can write a path integral depending on J of the operator O by adding in the path integral into E minus S, adding plus integral J O at X. And then we can write Green's functions for these operators in the same way as we did when we had just fields. So for fields, I would write Green's function that would be vev of phi at x1, phi at x2, until phi at xn. But since the operators, as I said, are composite, so they involve the fields, perhaps with some other objects, derivatives, and so on. So you can, let's say, the operator for as an example, an operator being the product of phi 1 to phi n at x, then the operator, the vev of the operator x is the vev of phi at x1, phi 1 at x1, until phi n at xn, when all these x's are equal and equal to x. So this would be the endpoint function of the field at all positions equal and equal to x. That clearly diverges, as I said. And then, so the Green functions of the operators are, of course, obtained in the same way as we obtain from the path integral from the partition function, are obtained in the same way as we obtain the Green's function for the fields, by taking derivatives with respect to the source. Right? So if here I take derivative with respect to j, I get phi down, so I get the Green's function for phi's, the Green's functions for phi. And similarly here, I take derivative with respect to jo, then I get jo down, so I get the Green's functions for, I get O down, sorry. So I get the Green's functions for O. But of course, because of this extra divergence that I said, these Green's functions, even at the different, when the operators are the various operators in the Green's functions have different values of x, it's not well defined, because, well, so even if there's one x, it's not well defined. There's this divergence in here. To make better sense of this, we'll use renormalization, that is described next, and the operator product expansion. Now, well, renormalization means that first we have to regularize and then do something else. But how do we regularize? Well, a simple method of simple and obvious method of regularizing. Sorry, somebody wants to get in, I guess. Yeah. So a simple and obvious method of regularizing is to reverse the composition of the O. So the composition of the operator O is to say that the product of the fields is all defined at a single point x. But now the regularization is called point splitting, is literally to split the point x into n points, x1 to xn. That is to reverse this. So instead of over x, I would write phi of x1 until phi of xn, right? And then we'll say that these x1 to xn are each very close to x, but yet different, and different between each other. Now, so we have extra divergences, but we have also a different feature for these composite operators, which is operator mixing. So it's possible that there are Feynman diagrams in terms of the fields that compose the operators. There are Feynman diagrams that mix these operators. Now, for this to happen, the operators that we're trying to mix will need to have the same charges under the symmetries respected by the Lagrangian, because the Feynman diagram is created using the interaction Lagrangian, and the interaction Lagrangian should suppose to respect the symmetries. So this is only possible if operator mixing is only possible if the operators have the same global charges. So the renormalized operators then, so this operator being defined as in terms of some fields phi j. I mean, here I said I consider a single field phi, but in principle there could be different kinds of fields in the operator. And then there could be, so these operators, as I said, are renormalized, so depend on the coupling in particular. And and it could depend on other things. So when we renormalize, we of course renormalize the fields, wave function renormalization. We renormalize the coupling through Zj. But as I said, we also need an extra renormalization that is intrinsic to the operator itself. And that is due to the divergence. So the renormalization is an infinite factor that we try to absorb in the physical object to get the physical object. But so there's an extra divergence due to the operator being composite. And so there should be an extra renormalization for the operator. And moreover, as I said, there's this operator mixing. So it's not that ON is Zn ON renormalized, but in fact, they can mix. So ON is ZnM OM renormalized with sum over M. So as an example, let's look at Yang-Mills theory. So in Yang-Mills theory, we have the gauge fields and the coupling. And so in a composite operator, I would renormalize the gauge field with Z3 to 1/2. I would renormalize the coupling with Z1 over Z3 to the 3/2. These are the things that we already found. But then I would also, in order to write a renormalized operator, I'd also add this matrix renormalization matrix ZJK, multiplying OK renormalized. And the renormalizations of these renormalization factors, Z and M, can be defined by Feynman diagrams with insertions of the operators, the corresponding operators, OJ and OK here for ZJK. And as we see, the renormalization is multiplicative in the same way as it is for the fields, coupling, and so on. It's not additive. It's not additive like for the ground state energy, let's say. For the field, it's multiplicative. For the operator, it's multiplicative in the same way it's multiplicative for the fields and couplings. So in general, this renormalization matrix factor Z and M is non-trivial, different than delta and M. But in the particular, there's one exception. Well, so when we have some conserved current of some symmetry, then the renormalization factor is 1, or I should say delta and M. That is to say that the conserved currents do not renormalize. And to see an example of that in QED, the word Takahashi identity says that, so in X space as opposed to momentum space, says that the derivative with respect to Z mu of this vev of psi bar with J mu of Z inserted is minus IE delta of X minus Z, 2-point function of psi bar, plus IE delta of Y minus Z, 2-point function of psi bar. So you see, if you normalize the field psi by ZR, on the right-hand side, I will have just these ZRs. And on the left-hand side, I would have the same ZRs on psi and psi bar. But then in principle, I imagine that I should have also some Z and M, ZJ k rather, I should say. But that's impossible because I don't have that on the right hand side. So that means that really Zj is 1 or Zjk is delta jk. All right, so we have this renormalization factor matrix. So OK is Zjk, OK renormalized. But so with a renormalization factor, for the fields, we know that we have an anomalous dimension for the field. Now, similarly, with this renormalization factor matrix for the operator, there is a notion of an anomalous dimension, just that now it's an anomalous dimension matrix with the same indices, right? So now I write the same kind of relation for the anomalous dimension. I would write like gamma is 1 over z lambda dd lambda z, just that now this is a matrix relation. So now I have a anomalous dimension matrix, gamma ij, is by definition the matrix Z inverse times lambda dd lambda, the matrix Z, all with, this is a product, and then within this is ij. So 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 for the field, this anomalous dimension matrix, this anomalous dimension was was a number. So and the number really meant that the field now did not have the momentum, the mass dimension, did not have the mass dimension, classical mass dimension, but had classical mass dimension plus this anomalous one. But now this is a matrix, so I have to consider the eigenvectors of this anomalous dimension matrix. So I have to consider the eigenvector, value problem. So, and then I consider the eigenvector On, which is an operator for this matrix. And the eigenvalue for this eigenvector will be the classical dimension of the eigenvector, delta 0, plus the anomalous dimension, gamma n. So for this eigenvector, I have the same thing as the same behavior as for the fields. So that means that for the scale for the 2-point function, for instance, for a scalar, so that I don't have some Lorentz structure, for the 2-point function of the operators On renormalized is understood as the 2-point function with these z factors, but this is an eigenvalue. So then that means that this should have the dimension 2, there are 2 operators, times the classical dimension delta 0 plus gamma n. So that means it has to be, and since it should depend on x minus y, it should be some constant divided by x minus y to the power 2 times delta 0 plus gamma n. So the dependence on x minus y is from translation invariance, of course. Oh, yeah. I mean, sorry. So strictly speaking, yeah, this result is only true in scale invariant theory, because otherwise I could construct the dimensionless object M, where M is some mass scale in the theory, times x minus y. But of course, if x minus y is small enough, then m times x minus y is much smaller than 1, so irrelevant. So that means that this is always true, at least at x minus y extremely small. A non-trivial example of a composite operator in QCD is the Quark mass. The Quark mass that Quark mass term, I'm sorry. So Q bar Q multiplied by M. And Q bar Q, the Quark Q bar Q would have a VEV, and that's what I call the Quark condensate. So it's a non-trivial object. And it renormalizes. So as I said, this is supposed to so obey. Since it's renormalized, it will must define a renormalization via a renormalization prescription at some scale, and let's call this mass scale at which we renormalized M. So at which we give the renormalization condition. So for instance, let's consider the endpoint function with some quarks. So I have the operators Q bar Q at Z1 up to Q bar Q at Zk, but then I also introduce some quarks Q at X1 to Xn and some Q bar at Y1 to Yn. So then this endpoint function would obey the same kind of renormalization group equation that is a natural extension of the one for the fundamental fields. So I still have m ddm, where m is this mass scale at which we renormalized, plus beta ddg, plus 2n gamma coming from these insertions of these fundamental fields q and q bar, 2n of them, each with anomalous dimension gamma. But now I also have k operators q bar q, so I should multiply also by k times the anomalous dimension gamma q bar q for the fermion for this composite q bar q. So this object acting on a green function should be 0. I will also define a mass depending on the energy scale, m bar, depending on q, in the same way as we define it. We defined it in the normalization group for the fundamental fields. So also like there, dd log of q over m of m bar is this anomalous dimension times m. Just as now, m is the object multiplying the operator in the series, so the anomalous dimension is gamma of q bar q. And the boundary condition is defined at so the normalization prescription is at the scale capital M. So therefore, the boundary condition for this differential equation is for m bar at capital M is equal to m. And then we can do a perturbative calculation in QCD that I will not reproduce here, and you find the dependence on this m over q written here. So at one loop, right? So it's m at 3 level, and 1 times 1 plus 8 g squared over 4 pi squared, the the usual factor, one loop factor, times log of n squared over q squared. All right, so let's understand what it means to calculate the anomalous dimension of an operator. So let's give a simple example for that, because maybe this seems a little confusing. It's certainly something new, so let's give an example. So let's consider our standard 5 to the 4 theory in 4 dimensions, where lambda, the coefficient, is dimensionless. And let's consider the simplest composite operator possible, which is just phi squared at point x. And we want to calculate the 2-point function of this operator. So that is to say, the vev of O at x with O at 0. So let's write, to calculate an anomalous dimension, we have to write Feynman diagrams. So at the tree level, it means I don't have any interactions. I only have propagators. So we represent the operator by sort of point splitting, if you want. We think of it as being regularized by point splitting. So we write a phi at a point on the sheet, and another phi at another point on the sheet. But we represent this line as being all of it 0, operator O being at 0. Right? And then for the other one, other operator at x, in the same way, we imagine kind of point splitting regularization. So we write it on the sheet as a line between 2 points, but this line is supposed to represent the operator at point x. Again, connecting one phi with another phi. And then obviously the tree-level diagram is just writing a propagator connecting 0 with x here and 0 with x here. So the Feynman diagram then has just these 2 propagators, right? And since the propagator in 4 dimensions is 1 over 4 pi squared times 1 over x squared, then the tree-level 2-point function is, well, so of course I have 2 fields at x and 2 fields at 0. So I have this Feynman diagram, but I also have the crossed one when I connect this phi with this one and this one with this one, right? So I have 2 ways of connecting. So I have a factor of 2 times this propagator squared. That's the tree value of the 2-point function of operator O. And now let's go to the loop level, to the 1 loop level. Well, 1 loop level means introducing means order lambda, so introducing a vertex at some point x. So I have the same 2 lines. So this line for the operator at x between 2 phis, and this line between 2 phis corresponding to operator at 0. And then I have also the vertex at z. Now I'm supposed to write Feynman diagrams, and you can see that there's only 1 Feynman diagram you can write, because this is a 4-point interaction. So I connect with the 2 lines here with the 2 phis here, and the 2 lines here with the 2 phis here. Of course, there's a combinatorial factor which just cancels the combinatorial factor of the in the interaction. So interaction is lambda over 4 pi, lambda 4 to the phi to the 4 divided by 4 factorial. So I just cancel that for factorial. That's it. But so then the Feynman diagram is just this vertex lambda, and now I have what? Well, I have 4 propagators. So 2 from x to z. So this is one. This is the second one, and 2 from z to 0. This is one. This is another. Right. And then, of course, in the Feynman rules, I also have integration over z. So I have lambda integration over z, this 1 over 4 pi squared to the 4, and then 1 over z to the 4 from operators from z to 0, and 1 over x minus z to the 4 from the propagator x to z. And let me define this as lambda times the 3 value, this one, times some function that I call it j of z, j of x, sorry. So by comparing, so just dividing with this and with lambda, I see that j of x is x to the 4 divided by 4 pi squared times integral d for y 1 over y to the 4 x minus y to the 4. And you can see that this is divergent. This is divergent when, for instance, when y is equal to 0, right? Y is equal to 0, then I have integral d for y over y to the 4. That's divergent, in particular log divergent, you think. And also when when y is equal to x, I also have integral. You can think of this as integral d for y is the same thing as integral d for y minus x over y minus x to the 4. So it's also log divergent. So I have to introduce some regulator, some UV cutoff. UV because, you know, small x means high energy, UV. And by the way, so at large y, this is not divergent. This is not infrared divergent. Large y means small energy, which would be infrared, right? Large y, this is just integral d for y over y to the 8th. So I only have this UV divergence. With corresponding, I have to introduce this UV cutoff or regulator, lambda. And then I leave it to you as an exercise to calculate that this is actually equal to 1 over 4. With this regularization, this is equal to 1 over 4 pi squared log modulus of x times lambda. So all in all, then we can write that up to one loop, I have the 2-point function of operator O of x with operator O at 0 is the 3 value of operator O of x with operator O of 0 times 1 plus lambda j of x, and this is j of x. So 1 plus lambda times this log of x lambda divided by 4 pi squared. But now let's understand what this means. So I told you that, well, this operator is thought of as the eigenvector of the anomalous dimension matrix. So the 2-point function of the operator behaves like the 2-point function of a fundamental field. That is to say, it's some constant divided by modulus of x. So this would be, otherwise, this is modulus of x minus 0, that is modulus of x, to the power 2, because we have 2 operators, times the total dimension delta, which is the classical dimensional delta, plus the anomalous dimension. And I write the anomalous dimension as delta minus delta 0. So I write C over x to the 2 delta 0 plus delta minus delta 0. But then this power law, I can always write the power law as exponent minus this times log of the thing. So I write it as exponent minus 2 times delta minus delta 0 log of x. But of course, x is dimensionful. So what I mean by log of x is regularized with lambda, and then I have log of x times lambda, the regulator, right? So so the 2-point function then is equal to this. But then delta minus delta 0 is supposed to be small. We're doing perturbation theory in lambda, and I know that delta minus delta 0 is supposed to be of order lambda then. So it's small, so I can expand in it, the exponent, and then I get 1 minus 2 times delta minus delta 0 log of x times lambda. Okay, but this c over x to the 2 delta 0 is just comes just from the 2 propagators, so that's just the 3 value of the 2-point function of the operator O. Okay, so the non-trivial part is this thing that multiplies the 3 value c over x to the 2 delta 0. So I compare now the 2 calculations. Sorry. Yeah, I compare this with this. I see the common 2-point function at 3 level, the common one, and then I identify this with this. And indeed, I see I have log x times lambda as I expected in here. And so that means that delta minus delta 0 is lambda over 4 pi squared divided by a 2 and times a minus. So minus lambda over 8 pi squared. And delta 0 is 2. So delta is 2 minus lambda over 8 pi squared at 1 loop level. All right. So this was a calculation of the anomalous dimension. Now let's do a calculation of operator mixing. Okay, so here I assume that there's no operator mixing. I assume that that O is an eigenvector. But we can see that, in fact, phi squared mixes with phi to the 4. So the same logic, I write phi squared, so the mixing between phi squared at x and phi 4 to the 4 at 0 is represented by the Feynman diagram, where I point split, at least on the sheet on which I draw, I point split the operator phi squared as a phi at a point and another phi at another point connected by a line. This still represents the operator O at x. And then the other operator at 0, phi to the 4, point splitted with a phi here, a phi here, a phi here, a phi here, connected by a line. And then the order lambda Feynman diagram is where I connect one of the phi's at x with one of the phi's at 0. But then from one of the phi's at x, I connect with the vertex at point z. And then the remaining 3 lines on the vertex are connected with the remaining 3 phi's. There's a combinatorial factor in here of 2 to the 2 times 4 to the 4 factorial. Why was that? Let's see. So there's first a choice which phi I connect with. So there's so this 1 phi here I can connect with 4 here. Then the remaining one I connect here. And then I have 3 possibilities to connecting the one here with the remaining 3 and 2 possibilities. So I get 4 factorial. And the 2, yeah, the 2 is because, yeah, the 2 is because I can have either, I can also cross the line. So I can like this and this, I guess. Well, okay, I don't remember exactly how to count the extra factor of 2. But anyway, so I have 2 times 4 factorial times lambda, and then this propagator from 0 to x. So 1 over 4 pi squared x to the 4. Then the propagator from x to z. Oh, and sorry, and I want to define this as in terms of the tree of this tree Feynman diagram. So just the product of 2 propagators from 0 to x. So I divide by an extra 1 over 4 pi squared, 1 over 1 over x squared. So I get, and then the remaining result I call I tilde of x. Then this I tilde of x is this x to the 4. No, wait. No, there's something wrong here. No, this should be x squared, I think. I think this should be x squared. Or not. So I have 1 propagation. So overall, I'm supposed to have 1 over x squared. Yeah. So yeah, maybe I can put here x to the 6 and then define this as x4. That's one possibility to fix this. But then I have 1 propagator from x to z. So this is 1 over x minus z and 4 pi squared. And then 3 propagators from z to 0. So 1 over z sixth. And integrated over z. And again, I can do a calculation, which I'm not sure if I gave as an exercise, but I can do a calculation and find that this integral written here is minus 2 pi squared, a regulator lambda squared over x squared. And again, that's because I have a UV divergence at z equal to 0 and z equal to, no, just z equal to 0, right? At z equal to 0, I have integral d4z over z6. Yeah, at z equal to x, I don't have a divergence. And this is only UV divergence. IR divergence at large z, I don't have, because again, this would be at large z, would be d4z over z to the 8. And then the corresponding I tilde of x. Yeah, so the integral, sorry, the integral is this one, the integral being having dimension 4, and the dimension is correct here. And then this I tilde of x with the corresponding prefactor is given here. All right. The operator product expansion. So I said that operators, these composite operators, have some divergences of themselves. But also when two operators go close to each other, I have a divergence. I mean, that is the point of writing here. Well, I mean, explicitly, for instance, we've seen here that two-point function of operator OX and OZ was proportional to 1 over x to delta. So this is divergent when x goes to 0. Right? So yeah, in general, an n-point function will be divergent the same way as when points goes together, the same as the n-point function of fundamental field is divergence when the points in the fields go together, go close to each other. So but the divergence is in x, right? So the divergence is in the position. But on the other hand, if I don't take a VEV, if I consider only the product of the operators, this is still an operator, right? That I can multiply with other operators or make a VEV of. So when two operators go together, on one hand I have a divergence. On the other hand, this is an operator, and that means that I can think of this as operators or disturbances in the vicinity of the operators, but with divergent coefficients, right? So I can think of this as some divergent coefficients times an operator based in the vicinity of these operators. For instance, I can say at 0, and then the coefficients will be depend on x and would be divergent when x goes to 0. Okay. In general, let's say, so by translation invariance, I can say operator at x with product with operator at y should be some operator. Let's choose it to be in the vicinity. Let's say, let's choose it at y times a coefficient function depending on x minus y, which would be divergent when x minus y goes to 0. But of course, what operator it is, I don't know. It doesn't necessarily need to be any one of these two. It's some operator. So what I know for sure is that there's a sum over the operators in the theory times coefficients Ci, J, K, so with operators K. Now in here, what I meant when I wrote the sum over K with operators OK is that there's a complete set of operators in the theory, OK, that so they are complete under the procedure, under this procedure of products of operators. So this equation that the product of operators goes to when, or is equal, approximately equal to when x minus y goes to 0 to this, is known as the operator product expansion by obviously y. There's an operator product and it's expanded into the complete set. And as I said, these coefficient functions are C numbers, not operators, and they're singular when their argument goes to 0. Now, this is an operator relation, which means that it should hold for any matrix element. And then, in particular, so that means that in particular, I can I can think of as I can think of as on vevs, and then in the vev of these, I would get the dimension of the operator OI and the dimension of the operator OJ, which means classical dimension plus anomalous dimension. And in the operator OK, I'll also get, for the vev, I would also get the dimension. On the other hand, this so and by translational invariance, this would be something that will depend on x minus y, and this would be also something that depends on x minus y, that is divergence. So by analyzing then the dimension of this should be dimension of the operator I plus dimension of the operator J minus the dimension of the operator K. But since it goes to 1 over x minus y at very small x minus y, then it should be 1 over x minus y to the power delta I plus delta J minus delta K. So then when I do this operator product expansion, that means that as an approximation, I can always approximate with the coefficient function that is most divergent times an operator. So I can consider only the operator that has the lowest dimension. So lowest dimension, so the highest in power in here. And then plus less singular terms. That particular fact makes this very useful for calculations. So, of course, if I would have to introduce all of the possible operators in the theory, the complete set, that would be a nightmare. But since I can approximate with the most singular coefficient times the corresponding operator, that makes it very useful. On the other hand, perhaps I do know the complete set, and then in a Green's function, which has an insertion of operators and then maybe some fundamental fields, I can write the operator product expansion of this OI with OJ, which is the sum over k of coefficient functions Cij(k) of x minus y, and then times the operator in the corresponding VEV. And now you see that I've reduced the VEV with 2 operators to the VEV with 1 operator. And so if I do know the OPE, which means if I do know the coefficient functions, then for all k, that means I basically have solved the theory, because I can iterate this fact and I can calculate the Green's function or VEV of any product of operators. Right? I write the VEV or Green's function operator OI at x or j at y, and so on until OP at w. And I do it operator product expansion iteratively. So I first do OI with OJ into OK, then OK with OL into OM, and so on until I'm left with a single operator, VEV, and then just a bunch of coefficient functions. And then I can, for instance, normalize the 2-point function, OP with OQ, as being a number C times delta PQ over x minus y to the 2 delta Q being the dimension of this operator. That means that in particular, using the OP inside the 2-point function, that means that and using the, so you use the OP inside the 2-point function, and then after that I use the fact that the operator VEV is can only be is thought of as the 2-point function of an operator with an identity operator. So that means is delta R1. So that means this CPQPR times operator R VEV is CPQR times 1, which is just this, C delta QP over x minus delta to the 2 delta Q. So I can just replace the 2-point function or the 1-point function, if you want, in the last iteration of the OPE, and completely describe the endpoint function, the Green's function of OPEs in terms of coefficient functions and this normalization factor C. Okay, so the knowledge, the complete knowledge of the OPE is enough to the complete knowledge of the OP is enough to solve the theory. Of course, so there's one thing that I haven't discussed. So yeah, maybe I said it here. So these coefficient functions. Oh yeah, I said it here. So there's no mass scale. So in a theory with no mass scales, the coefficient functions go to 1 over x minus y times this delta 1 I plus delta j minus delta k. But of course, if x minus y is small enough, then m times x minus y is much less than 1, which means you can be ignored. Another way of saying is that if you are at energies much higher than the mass scales in the theory, it's as if you don't have mass scales. And then you can write this, okay? So that means that the coefficient functions at very small x minus y are completely known, even in a theory with mass scales. So one example. So let's take one example, which is in QCD. That is, well, the most relevant theory in which you can do calculations. So in particular, let's think of the 2-point function of the currents. So J nu at x and J nu at y. So the product of two currents, J mu at y and J nu at x and J nu at y. Then we can do so. These currents are protected, so they don't have anomalous dimensions. But the product of two operators is still expanded via the OPE into the complete set of other operators. Of course, if I write the OPE, the maximal contribution would be from the quark current Q bar gamma mu Q, right? So the product of two currents would have the maximal contribution from the quark current. On the other hand, by symmetry, by Lorentz symmetry in particular, we know, or you can prove even rigorously, that you can expand the operators in irreducible representations of the Lorentz group. So that means that the complete set of operators with the of gauge invariant operators for the OPE with the same charges in the same category. So for the OPE of these two currents must be this operator OF of nth order with indices mu1 to mu_n, which is Q bar gamma mu1 Q. F here is some flavor. some flavor of Quark. But then inside, together with the gamma mu, I also insert covariant derivatives d mu2 up to d mu n. And for it to be an irreducible representation of the Lorentz group, I must symmetrize the indices mu1 to mu_n and take out the traces. So, so the symmetric traceless product of vector indices is an irreducible representation of the Lorentz group. So if I don't have these D's, then I have this current Q bar gamma mu Q. So as I said, this is the leading contribution to the product of two currents. And then and this one has dimension 3 because, well, the kinetic term would have an extra derivative d mu, and the kinetic term has to have, any term in the Lagrangian has to have dimension 4. And then when you introduce covariant derivatives, they are covariant in order for this operator to be gauge invariant. So with the product Q bar to the left and Q to the right, I make a gauge invariant object. And then each derivative has dimension 1. So the total dimension of this object is n plus 2. So it's 3 plus n minus 1, n plus 2. But the Lorentz spin, that means the irreducible representation of the Lorentz group, is n, since there are n vector indices symmetrized and with the trace subtracted, a vector index corresponding to a spin 1. Okay. Then that means that in momentum space, the OPE of the 2 point of the two currents is, so I have J mu at x with J mu at 0 in momentum space, so Fourier transform. It's written as a sum over these operators ON, ONF. This operator ONF, however, have dimension n plus 2, as we said, whereas this thing has dimension okay, so the current has dimension 3, 6 minus 4, 2, dimension 2. So I have to add something of dimension 2, which is the q squared, capital Q squared, I think, is minus q, little q squared. Q squared for the quarks in order to obtain this dimension. But then I have to cancel this dimension n plus 2 of the operators. And I also have to cancel the Lorentz indices. So so I put 2 of the Lorentz indices, so mu and nu I put on the operators. That's how it's supposed to be. But then the rest of indices, n minus 2 indices, have to be cancelled by, and I can only cancel them with the momentum q. So I have this q1 up to q, and q mu1 up to q mu n minus 2. I'm not sure why the 2 factor. I guess there's some convention here. But then for dimension reasons, I have to divide by the same q squared to the power n-2, right? So the power in here is 2n-2. But then the power in here is n-2. So 2n-2, subtracting n-2 from 2n-2, I get n. Okay, so that's not right. 2n-2, I get n. This is mention of this thing is supposed to be n+2. Oh yeah, sorry, no, yeah, that is right. So dimension. No. Dimension of this is, yeah, it's 6 minus 4, 2. But then dimension of this is 2 times 2. That doesn't seem right. The only thing I can think of, well, okay. Anyway, I'm confused about here. So I guess so. Either the power here or the power here should be different. Yeah, and so the indices mu nu can be either on the operator or on a g mu nu. So that's kind of a trace or something, if you want. So it's an operator. It's still something of this form, just with operator with mu1 up to mu-n, cancelled by q mu1 up to q mu-n, then divided by q squared to the n. So this is the leading piece, and then there are other sub-leading pieces that one can add. And the next space, I would write the product of these two things as so the operator itself, as I said, but then the operator would have dimension n+2, and the corresponding object with indices. So I have to multiply with x mu1 up to x mu-n-2, and divide by some power of x such that dimensions work out. So this has dimension n-2. And from this, I would have n-4. So sorry, this has dimension 2 minus n. And then plus 2, so 4 minus n. With dimension n+2. I get dimension 6. Okay, so this works out. This doesn't seem to work out. Okay, this also works out for the same reason. And then, of course, the coefficients in here are just numbers. They should not be functions of x. I'm sorry. Yeah. Sorry. Completely sorry. Yeah, this QF here's yeah, dimensions work out, because this is the dimension in here is n+2 minus n-2. Sorry, and the dimension in here is 2n-2, but then from this I subtract n-2, so I have n. The dimension here is 2. No, it doesn't work out. All right, something is wrong in the dimension here. And I think this is supposed to mean the charges of each flavor, charges squared of each flavor, because each flavor corresponds to with a different charge. So yeah, I think the power in here must be wrong. Anyway, the power in X space is certainly correct. And the numbers Cn in here and Cn tilde in here are just that, numbers. They don't depend on anything. And I can also put mu equal to nu and sum over, and then have so if I put mu equal to mu in the operators in here, corresponds to some d slash, but then d slash acting on q will give some mass of the quark times, via the equation of motion, will give some mass times q. So this thing will cancel, right? So the mu nus will cancel, and I would get something with n-2 indices. And the same n-2 indices as on the x's, but this is the same type as this sum. So in other words, is just one sum, this sum with x's contracting all the indices on the operators. Then on the other hand, I had so these were numbers, but when I said d slash on q gives some q, is proportional to some q, but of course the mass is renormalized. So so in the quantum theory, this the resulting coefficients will get a dependence. So once I use that contraction with this slash, I will get some coefficients that depend on alpha s and on the scale mu. But nevertheless, it's a dimensionless function. Now, until now, I said I talked about OPE, and I said that it's a expansion in the modulus of x. Now, if you're in Euclidean space, that clearly means x going to 0. So that's what we meant. We meant an expansion in Euclidean space so before we meant an expansion in Euclidean space. Vic rotated to Minkowski space, which meant an expansion really in x going to y, or x going to zero, in which we keep the operator of lowest dimension. But in Minkowski space, modulus of x going to 0 is not the same as x going to 0. So in particular, we can have modulus of x squared equal to 0 thought of as a light cone with x finite. So we can then have a different kind of OPE where x doesn't go to y, but rather modulus of x minus y goes to 0 with x minus y finite. That would be a light cone expansion near the light cone. In that case, the relevant dimension for the expansion is not the dimension of the operator with indices OF with indices mu1, mu_n, but rather the dimension of the full object in the numerator, the thing that doesn't have Lorentz indices, right? So this is something with dimension. And then x mu1, x up to x mu_n is still finite, even though x squared is close to 0, right? So really the operator that we're thinking of is x mu1 up to x mu_n up times this operator. So the dimension of this is the dimension of O minus the dimension of n, since the dimension of an x is -1. So dimension of operator minus n, where n is the number of vector indices, means the dimension of O minus the spin of O, since O has spin n. Dimension minus spin is called twist, T. So in the case of the quantum theory, the twist T is delta, the total dimension, minus S, total spin. So in the OPE, when I think of this as an expansion, the expansion is not anymore as in the expansion, I don't keep the leading, the operator of leading dimension anymore, of smallest dimension anymore, or leading dimension operator, but I take the operator of the smallest twist. So this is a leading twist operator. Okay. Now there's a different there's another thing to consider in the example of QCD, the mixing, operator mixing. So I talked about this particular operator with Quark, Q bar, gamma mu, derivatives Q. But this can also mix with an operator without quarks. That is, and to make it gauge invariant, at the end I have to have field strengths. So F mu1 nu at the one end, and at the other end F mu_n nu, with covariant derivatives in the middle and symmetric traceless. This has still dimension n+2, since so now I have in here n-3 sorry, n minus 2 Ds. So I dimension n minus 2 from this, and then dimension 2 from this, dimension 2 from this, total dimension n plus 2. And they also have spin n because they also have spin n because I have n indices in here. So you see I have mu1 up to mu n minus 1, but then I have n nu, which makes it an nth index. Sorry. No, sorry. Yeah, nu is summed over, so that doesn't count. And then I have free indices mu1 up to mu n, so symmetric traceless. That's still spin n. So the both dimension and charge, in this case spin, are equal. So there is a possibility of mixing. As I said, only operators of the same charges can mix. That means that in the OPE, both OGs can appear also the same as OFs. I wrote in here OFs, but I can also write OGs as well. And to see the mixing, I write the operator x at x as I consider, let's say, the operator with no covariant derivatives, and then at x I would have a gamma. I have a q at one end and another q and q bar at one end and q at another end. And operator at 0, OG, I'll have now a gluon at one end and another gluon at the other end, and again connected. So that's why I wrote this arrow in the sense that one operator has q bar, the other operator has q. But of course, I could still have covariant derivatives in the middle. And so there is the Feynman diagram that mixes them, which is for this for this quark line. So the quark goes like this into the anti-quark. And then here emits a gluon that connects with a gluon, here a gluon connecting with another gluon. Now, in principle, I could also have covariant derivatives in the middle, here covariant derivatives, and in the covariant derivatives there's a gluon, so the gluon could connect also with the corresponding gluon in the middle. So in any case, that means that all the operators OF mix with all the operators OG. All right, so this is an example of why we can mix all of the operators OF with all of the operators OG. Okay, so this is everything I wanted to tell you today. Do you have any questions? Can somebody check that you're still hearing me? Okay. All right. So if you don't have any questions, I'll see you on Tuesday at 10. All right. Bye.